Hello everyone, this is workshop 8, limiting reactants. So in the last workshop, in workshop 7, we were looking at how to balance chemical reactions. Because remember, matter cannot be created or destroyed, and so if you have a certain number of reactants, you have to have the same number of products in terms of like the mole ratios and the atom ratios. If my chemical reaction starts with 5 atoms of carbon on the reactant side, I should have 5 atoms of carbon on the product side. If I have, or rather moles, if I have 7 atoms or 7 moles of oxygen on the reactant side, I should have 7 atoms or 7 moles of oxygen on the product side. But when you're doing a chemical reaction, it cannot go on infinitely. At a certain point, the chemical reaction has to stop, and that often happens because you run out of your actual reactants. If you run out of reactants, the chemical reaction cannot proceed forward. You have ran out of the parts to actually make the final product. That is what the limiting reactant is. When you have your balanced chemical reaction and you're looking at the balanced stoichiometry of everything, the mole ratios of reactants to products, your limiting reagent is going to be the reactant that stops the reaction from moving forward. It is going to be the reactant that you have the smallest amount of, and therefore limits how far the chemical reaction can actually proceed. It doesn't matter how much of the other reactants you have. Those would be your excess reactants. You can have a lot of the other reactants, but as long as you only have a small amount of the limiting reactant, the reaction is going to stop once you run out of said limiting reagent. The textbook, I know, uses the example of like you're making pizza and you have to use like a certain amount of crust, a certain amount of cheese, and a certain amount of sauce. I'm going to just jump straight into a chemical reaction so you can see how it works with actual atoms involved. The pizza example is great. If that helps, it makes sense. That is amazing. But I want to jump in just right into a chemical reaction to see more of what we are talking about with these mole ratios. So let's say we have the reaction of 2 hydrogen gas, 2 moles of hydrogen, reacts with 1 mole of oxygen gas to produce 2 moles of water, gaseous water. So what this balanced reaction is telling us, is that you need 2 moles of hydrogen and 1 mole of oxygen to make 2 moles of water. And so based on the amounts that you have to start with, that is going to determine how much water you can actually make by the end of this. It says here, if we start with 10 moles of hydrogen and 7 moles of oxygen, what is our limiting reagent or reactant? I'm going to end up using those words interchangeably. What is our limiting reactant? What is our excess reactant? And how much excess is left at the end of the reaction? To figure out what is your limiting reactant, you have to know how much product each of your reactants is going to make. And that's why these balanced chemical equations are so important, because we now know the stoichiometry of everything. We know the ratio of reactants to products. Because it takes 2 moles of hydrogen and 1 mole of oxygen to make 2 moles of water, you can say that for every 2 moles of hydrogen, you make 2 moles of water. You can set up a mole proportion. 2 moles of hydrogen for every 2 moles of water. Same thing with our oxygen. It's a 1-to-2 ratio. 1 mole of oxygen makes 2 moles of hydrogen. With these balanced chemical equations, you can convert from moles of one substance to moles of another. We saw that a little bit when we were doing our combustion analysis. You were able to go from moles of carbon dioxide into moles of carbon, and moles of water into moles of hydrogen, because we know that there is 1 mole of carbon used to make 1 mole of carbon dioxide, and 2 moles of hydrogen needed to make 2 moles. To make 2 moles of hydrogen need to make 1 mole of water. The same thing is happening here. Our chemical reaction tells us how many moles of reactant are going to make however many moles of product. So as long as you can convert moles of reactant into moles of product, you can see what is your limiting reactant. And so if we are starting with 10 moles of hydrogen, we have our conversion factor here to convert into moles of water. And it's going to be just like dimensional analysis. We're trying to get out of our given unit and get into our desired unit. So moles of hydrogen will go in our denominator, so they cancel, and moles of water will go in our numerator, so now we can get to moles of our product. it's a 2 to 2 ratio, or 1 to 1, so 10 times 2 would be 20, but then divided by 2, you end up with 10 moles of hydrogen, making 10 moles of water. Now we're going to do the same thing with our oxygen. 7 moles of oxygen. We use a ratio here. We want to get out of moles of oxygen. We want to get 2 moles or into moles of water. And so we set up our proportion accordingly. But now it is 1 mole of oxygen to make 2 moles of hydrogen. 7 moles of oxygen is going to make 14 moles of water. We started with less oxygen, but based on the stoichiometry, we end up making more water from this amount of oxygen. And so your limiting reagent is not determined by how much you start with necessarily, because you can see here we're starting with more hydrogen than we are, oxygen, but it matters how much product it can actually make. The amount of hydrogen we're starting with can only make 10 moles of water, while this amount of oxygen can make 14 moles. And so hydrogen, because it is going to make less product, because the hydrogen is going to make less product, our hydrogen is our limiting reagent. The limiting reactant is based on the amount of product it can make, not how much you are starting with, which means oxygen is then going to be our excess reagent. We are able to make more product, and so this has to be our excess. Because again, it doesn't matter that oxygen can make 14 moles of water. If hydrogen is our limiting reagent and it only makes 10 moles of water, this reaction is making 10 moles of water. We are never going to hit 14 moles of water because we will run out of hydrogen before that can happen. So we have our limiting reagent, we have our excess reagent, and now we want to know how much excess is going to be left over. And so now you're going to kind of work backwards. If you know that you are only going to make 10 moles of water in this reaction because of our limiting reactant, we can figure out how much oxygen is required to make this amount of water, again, based on our stoichiometry. Once you know what the limiting reagent is, and you know how much product that limiting reagent is going to make, you can convert the smaller amount of product back into your now excess reagent to actually figure out how much excess or how much of that reagent was required to make this amount of water or whatever product you're working with. It's still a 1 to 2 ratio, but since we're going from water to oxygen now, we flip the equation. Moles of water goes on the bottom to get out of our given units, with moles of oxygen on top to get to our desired units. 1 mole of oxygen for 2 moles of water. To make 10 moles of water, 10 moles of hydrogen are going to react with only 5 moles of oxygen. We have 7 moles to start with, we're only going to use up 5 moles, and so the difference is going to be the excess that we have left over. 7 moles of oxygen minus 5 moles of oxygen. We have 2 moles of oxygen in excess. And so for all these problems, you should be able to find a limiting reagent, an excess reagent, and the amount of excess that you're going to have left over. And the last thing you are likely going to be asked for is then a percent yield. Percent yield we'll see in future problems. We're not going to be able to do it in the problem here because the equation for that is that percent yield is your actual yield divided by your theoretical yield. Oh, this is not going to fit, sorry. And then times 100 because it is a percentage. Actual divided by theoretical. What that means is that oftentimes in a chemical reaction, you are not going to get 100% yield. The value that you get when finding your limiting reagent is your theoretical yield. 10, right in blue, the 10 moles of water produced is the theoretical amount of water that can be made if all 10 moles of hydrogen react with all in this case 5 moles of oxygen. But oftentimes in a chemical reaction, you don't get that perfect, like that best case scenario. The 10 moles are going to react with the 5 moles of oxygen, but they might not all react completely. The reaction might not go in the forward direction long enough to make 10 moles of water. You might lose some of the energy in forms of heat. Oftentimes in a chemical reaction, you don't get that theoretical yield, and you get some value less than your theoretical yield, which is your actual yield. But there is no way to actually calculate an actual yield this way, unless of course they give you information over here. But in terms of just finding out what your limiting reagent is, if they ever want you to calculate percent yield, they would have to tell you what the actual yield is, because that's experimental data. You will do that in lab. If you're in Chem 102 or 103, you're going to see that you can find your actual yield of product and compare it to a theoretical. And that's actually what we do a lot in organic chemistry. That's what a lot of the labs come down to. You try to produce some compound, you figure out what your actual yield is based on mass values, but then there is a theoretical yield that you figure out with your balanced chemical equation. And so you compare the two values to see what your percent yield actually is and see how much product you were able to actually make versus what you theoretically could have made. And so we'll see percent yield in the questions coming up, because again, this value has to be given to you. Just from the information here, we don't know what our actual yield is because no experiment has actually been done. So let's jump into some practice problems. Starting with question 1. So adipic acid H2C6H8O4 used to produce nylon is made commercially by the reaction between cyclohexane and oxygen gas. So cyclohexane plus oxygen gas will give us our adipic acid and water. Assume that you carry out this reaction with 25 grams of cyclohexane and 75 grams of oxygen. Upon completion of the reaction, 33.5 grams of adipic acid is obtained. Label the limiting reactant and excess reactant, find and label theoretical yield, determine how much excess is left, and finally calculate the percent yield for the reaction with the information given. So there's a lot of different things they want us to solve for. Likely on the exam, you will not have to solve for all of these parts. You will be asked for which one's limiting, which one's excess, find the amount of excess, or find the percent yield, or find like XYZ information. But for practice, we're going to solve for every part that is possible for these types of problems. So the main thing, notice that they are giving us mass information. They're saying that we are working with 25 grams of our cyclohexane and 75 grams of oxygen. Remember, stoichiometry tells us about molar ratios. 2 moles of cyclohexane and 5 moles of oxygen make 2 moles of adipic acid and 2 moles of water. And so, just like when you're doing the empirical formula and you're doing combustion analysis, mass should always be converted to moles. There is not enough information that you could derive from the mass values on their own. We have to convert them to mole values first. So I'm going to erase the oxygen information just so I can do my calculations here. Let's get everything into moles first. So the molar mass of cyclohexane, I have it as 84.18. Remember, however many decimal places you end up rounding your molar masses to is going to change this value slightly. Your answer should still be within reason of the correct answer. Maybe off by some decimal places, but nothing too major in terms of differences in values. So 84.18 grams of cyclohexane for every 1 mole. I'm actually going to write out the oxygen calculation first before I move on to the next step. Remember, oxygen is diatomic, so when you're saying you have 1 mole of oxygen gas, you do not have 16 grams of oxygen, you have 32 grams of oxygen. And so now both of these calculations will get us into moles of our desired reactant. Now, oftentimes when you have a chemical reaction, in the example that I showed, there was 1 product. It was just water. So we know to convert both of them into water. When you have a limiting reagent problem and you have more than 1 product, it does not always matter which product you convert them to. In this case, we want to convert it to adipic acid because we want to find the percent yield of adipic acid. They told us information about the acid, and so we're going to convert both of these into our acid. If you're not being asked to find percent yield though, and they're not asking for a specific product, you can convert your reactants into either of your products. The main thing is that you have to convert both reactants into the same product. because we're trying to make that comparison to see which reactant is going to make less product. If I have this amount of cyclohexane and this amount of oxygen, how much adipic acid is the cyclohexane going to make and how much acid is the oxygen going to make? If I convert one of these reactants into adipic acid and the other reactant into water, I can't make that direct comparison between the two to see which one is making more or less product. So as long as you convert both of them into the same product, and the question is not specifying which product they want, you can choose either product to convert it to. But in this case, we have adipic acid information. We are going to convert to adipic acid. Put the equal signs when I don't need it. And so now that we have moles of each reactant, we are going to convert to moles of product like we did before. There is a 2-to-2 ratio between our cyclohexane and our acid. 2 moles of cyclohexane, we put in our denominator, creates 2 moles of adipic acid. And so let's get our mole values first. Actually, since they're asking about mass to begin with, we are not going to need the moles necessarily, so you can just convert this straight to grams if you felt like it. I'm still going to convert to moles first and then grams, just to make a future calculation a little bit quicker. But if you just want to do the entire setup of grams to moles to moles, and then moles to grams, you absolutely can. But I am going to take a pause here to do the math real quick. And so 25 grams of cyclohexane is going to produce 0.29698 moles of adipic acid. H2C6H8O4, and now I'm going to convert to grams just to have the mole value there. And so the molar mass that I have for adipic acid is 146.22 grams. For every 1 mole. And so when we convert from moles to grams, 146.22. 25 grams of cyclohexane produces 43.4 grams of our acid. And so now we're going to do all the same work for the oxygen. First, we convert grams of oxygen into moles of oxygen, and now we look at the ratio of oxygen to adipic acid. For every 2 moles of acid that get produced, 5 moles of oxygen are needed to produce this amount. So again, I'm going to convert it to moles first. And so we produce 0.9375 moles of our acid. And again, we have to convert to mass, so 146.22 grams for every 1 mole. And so for our oxygen produces 137.1 grams of our acid. So, first step of this problem is to just see which of these are limiting, which is our excess. Remember, it's based on the amount of product. Whichever makes less product is going to be our limiting reagent. In this case, cyclohexane only makes 43.4 grams, while our oxygen makes 137.1 grams, which means that cyclohexane is our limiting reagent. While our oxygen is our excess. And so that is the first part of the problem. So first we label limiting and excess reagent. Now we want to find and label our theoretical yield. Remember, theoretical yield is the amount that can be made based on the limiting reagent, aka the smaller of the two mass values that we get. Since our limiting reagent is cyclohexane, we can only make 43.4 grams of theoretical yield, 43.4 grams of our adipic acid. Even though this amount of oxygen can make 137.1 grams of acid, only 43.4 grams are going to be produced because we only have 25 grams of cyclohexane to work with. And so next, determine how much excess reactant is left. That is now working backwards. We know the theoretical amount of the acid that can be created, how much oxygen was needed to make this specific amount of acid. And that is why I calculated the mole values here, because again, you could have just gone straight to the mass value to figure out how much oxygen you needed. But then you would have had to have done this long multiplication process 2 times. First going from grams of oxygen all the way to grams of cyclohexane all the way to grams of acid, and then from there go from grams of acid all the way to grams of oxygen. By pausing in the middle of our calculations and finding moles first, we have skipped the first step. We don't have to convert 43.4 grams into moles because we already know how many moles 43.4 grams is. So we can skip at least a little bit of the math and make this process go slightly faster. But if you forget to do this and you go straight to mass of acid, it's fine. You can just do the whole process backwards. So it's not harming any of your calculations. This is kind of just a way to make things a little bit quicker. So we have 0.29698 moles of acid. Since we want moles of oxygen now, we go back to our ratio up here. We take our fraction and we just flip everything. 5 moles of oxygen are needed to produce 2 moles of our acid. We started with a mass value, and so we have to get this back into a mass value, multiplying now by our 32 grams of oxygen. And so 0.29698 times 5 divided by 2, and then times 32. To make the 43.4 grams of adipic acid, we only need 23.8 grams of oxygen. We don't need a lot of oxygen to make this amount of our adipic acid. And so if we know that we can make, I'm actually gonna do the calculation over here to save some space. If we know that we can make 43.4 grams of adipic acid, and we only need 23.8 grams. Oh, sorry. That's not how the math works. We're trying to calculate excess. Sorry. We know that we have 75.0 grams of oxygen. We are only going to use 23.8 grams of that oxygen. And so we will have 51.2 grams of oxygen left over by the end of this reaction. So we have our theoretical yield. We know what our limiting reagent and excess reagent are. We know how much excess we have left. And so now the last part is to calculate the percent yield. And this is what I mean, where they had to give us the actual yield for this problem. They told us that upon completion of the reaction, 33.5 grams of adipic acid is obtained. We know that theoretically, if all 25 grams of cyclohexane reacted, we would make 43.4 grams of adipic acid. But they are telling us we only obtained 33.5 grams by the end of the reaction. The reaction did not proceed to completion, and so we did not get all 43.4 grams of adipic acid. And so the actual yield given to us in the problem is 33.5 grams. We divide that by the theoretical yield. We could have produced 43.4 grams, and we multiply that by 100 because percentage. And so the actual percent yield of this reaction is 77.2. By the end of this reaction, only 77.2% of the possible adipic acid was produced. So yeah, there are a lot of calculations in these type of problems. On the actual exam, you will likely not be asked to solve every part of this, but you have to be comfortable with all of these calculations. Finding limiting reagent versus excess reagent, knowing what your theoretical yield is, finding your excess, finding your percent yield. So let's go on to problem 2. Problem 2 says consider the reaction which converts iron ore into iron. So iron oxide plus carbon monoxide gas, or 3 carbon monoxide gas, becomes 2 iron and 3 carbon dioxide. Assume this reaction is carried out with 1.50 times 10 to the second grams of iron oxide. I'll give myself a little bit of space. Let me just write this. We know we're going to do multiplication in a second. And so I should have enough space right here. And 512 grams of carbon monoxide. And that upon completion of the reaction, 87.9 grams of iron is recovered. I don't know why I said it like that, sorry. Label the limiting reactant and excess reactant, find and label the theoretical yield, determine how much excess is left, and calculate percent yield. So same as before, solving for every part. So first things first, finding that theoretical yield, finding our limiting and excess reagents. We are starting with grams once again, and so of course we have to convert into moles. 1 mole of iron oxide. I have a mass of 159.68 grams. And for the carbon monoxide, 1 mole of carbon monoxide, I have a mass of 28.01 grams. So getting both of these out of grams and into moles. So now, starting with our iron oxide, looking at that stoichiometric ratio. Iron oxide to iron, since that's what we're trying to recover, it is a 1:2 ratio. 2 moles of iron are going to be produced from 1 mole of iron oxide. And we'll stop our calculation there for the same reason as before. 1.50 times 10 to the second, divided by molar mass, and multiplied by 2. 1.50 times 10 to the second grams of iron oxide produces 1.8788 moles of iron. And now converting that into grams, 1 mole of iron, it's I believe 55 point something. 55.84 grams. .8788 times 55.84. So 1.50 times 10 to the second grams of iron oxide allows us to recover 104.91 grams of iron. Now moving on to the carbon monoxide, doing the same work with our different ratio. We are in moles of carbon monoxide, and we need to get to moles of iron. There is a 3:2 ratio now between our carbon monoxide and iron. 2 moles of iron are produced from 3 moles of carbon monoxide. Times 2 divided by 3. And so 512 grams of carbon monoxide produces 12.186 moles of iron. Converting that to mass, times 12.186 times 65.84. This much carbon monoxide produces 680 0.47 grams of iron. Looking at our limiting and excess reagents, the iron oxide only makes 104.91 grams of iron, while the carbon monoxide makes 680.47 grams. Smaller amount of iron produced, so iron oxide is our limiting reagent. Where's the cap? While the carbon monoxide is our excess reagent. And if the iron oxide is our limiting reagent, that means that the 104.91 grams is our theoretical yield. We want to know how much excess is left, so we work backwards from our theoretical yield. We can only make 104.91 grams of iron, and so how much oxygen is needed to make that amount? We know that we already have the moles, and so we could start our calculations from there. This much iron oxide makes 1.8788 moles of iron. Again, you can start your calculations from 104.91. You don't have to take this pause in the middle. If you're more comfortable just going from the mass all the way back to the carbon monoxide, that is completely fine. Looking at our mole ratio again, if we have moles of iron, we're trying to get back into carbon monoxide, and so we flip the fraction that we have here. 3 moles of carbon monoxide are needed to produce 2 moles of iron. And then we take our mass ratio here and again flip it. Since we are in moles of carbon monoxide, we need to multiply by molar mass to get back into grams. (1.8788) times 3 divided by 2, and then multiplied by its molar mass. And so only 78 point, where we rounded to 36, only 78.9 grams of carbon monoxide are actually needed for our theoretical yield. You only need 78.9 grams of carbon monoxide to make 104.91 grams of iron oxide. And so if we started with 512 grams, we're only going to use 78.9. That means that we have 433, for sake of because I'll leave it at 433 grams of carbon monoxide as excess. I keep not boxing the theoretical yield. Sorry about that. So we know our limiting reagent, our excess reagent, our theoretical yield. From our theoretical yield, we get the amount of carbon monoxide that is left over that is not going to react because we ran out of iron oxide for it to react with. And all that's left now is percent yield. 87.9 grams of iron is recovered, so that is our actual yield. But we know that if all 100% of the iron oxide reacted, we would produce 104.91 grams of iron. And so as a percentage, we have an 83.8% yield. You're going to notice a lot of this math ends up becoming a little bit repetitive, and that's good. The more repetitive it is, the more you can get practice with these types of problems and get comfortable doing the work. So let's move on to question 3. Question 3, when benzene reacts with bromine, bromobenzene is obtained. So benzene, bromine, bromobenzene, and then you end up making hydrobromic acid as a byproduct. And so 30 grams of benzene reacts with 65 grams of our bromine and 42.3 grams of bromobenzene is collected. Same as the last two. Limiting reactant, excess reactant, find and label theoretical yield, determine amount of excess, calculate percentage. So it's the same work as before. Getting these into grams, 1 mole of benzene. I have a molar mass of 78.12. And for bromine, 1 mole of bromine, similar to oxygen in the first problem, bromine is a diatomic element. You're going to double the mass that is on the periodic table. And so the mass of bromine, I have 159.808 grams. Starting with our benzene, we want to get to bromobenzene. I'm definitely missing a coefficient. Am I missing a coefficient? I don't know, this is all 1-to-1 ratios. So this reaction is a little more straightforward because you can see we have no coefficients to worry about. It's all 1-to-1. So this will make our math a little bit more streamlined. 1 mole of bromobenzene produces 1 mole of cyclohexane, or is produced by 1 mole of cyclohexane. (30 divided by the 78.12). And so 30 grams of cyclohexane is going to produce 0.38402 moles of cyclobromine. Converting moles to mass, the mass of cyclobromine, I have 157.014 grams. And so as a mass, 0.38402 times 157.014. 30 grams of benzene is going to produce 60.30 grams. Or I should be focusing on sig figs a little bit more. 60.3 grams of bromobenzene. Now we do our same work for our bromine. Again, it's a 1-to-1 ratio, so 1 mole of cyclobromine or bromobenzene, sorry, not cyclobromine, of bromobenzene is produced by 1 mole of bromine. And so for moles, 65 grams of bromine creates 0.4067 moles of bromobenzene. Converting that into mass, C6H5Br. Times 157.014. 65 grams of bromine is going to produce 63.9 grams of bromobenzene. These values are much closer than the last problems that we were working with, but we could still tell what is our limiting versus what is our excess. Where are my color markers? There we go. The benzene makes 60.3 grams of bromobenzene, while the bromine makes 63.9 grams of bromobenzene. And so our benzene is our limiting reagent. While our bromine is our excess. if benzene is our limiting, that means our 60.3 is our theoretical yield. Working with our 60.3 grams, we can now find how much excess is left. We know 60.3 grams is 0.38402 moles of bromobenzene. It is a 1-to-1 ratio, so 1 mole of bromine is needed to produce 1 mole of bromobenzene. And 1 mole of bromine is 159.808 grams. And so to make 60.3 grams of bromobenzene, we only need 61.4 grams of bromine. And so we have 65 grams to start with. We only need 61.4. And so in excess, we have 3.6 grams of bromine left over. I do not have the space to write excess, but we know that this is our excess reagent. So yeah, in this case, we don't have a lot of bromine left over. Our theoretical yield was very close to our excess yield, and so we know that a lot of the bromine is going to be used up in this reaction. And so last part is that percent yield. They told us that this reaction, 42.3 grams of bromobenzene is collected. So our actual yield is 42.3. We know that we can make 60.3 grams. And so as a percentage, we have a percent. Where mark go? We have a percent yield of 70.1. And the calculations become very repetitive very quickly, which means you get a lot more practice each time you go over one of these problems. Now, question 4 works a little bit differently. Hydrogen sulfide is an impurity in natural gas that must be removed. One common removal process is the Claus process, and it relies on this reaction here. Hydrogen sulfide reacts with oxygen to produce sulfur and water. It's a little bit similar to our combustion reactions. And so under optimal conditions, the Claus process gives 98% yield of sulfur from hydrogen sulfide gas. If you start with 30 grams of hydrogen sulfide, and 50 grams, 50 here, 50 grams of oxygen. How many grams of sulfur will be produced assuming a 98% yield? And then label limiting reactant and excess reactant, find and label theoretical yield, determine how much excess reactant is left. So a lot of this problem is going to work the same. We're going to start this process in a very similar way. We're still finding limiting reagent versus excess reagent. We're still finding how much excess is left over. We still want theoretical yield. But here, they want us to now find our actual yield. They're giving us a percent yield, and they are saying if the percent yield of this reaction is about 98%, how much sulfur are you going to produce based on the reaction that we actually have here? But again, we're going to start this process the same because we still need to know how far this reaction can actually proceed to know what the 98% is coming from. What is our 100% that we are not taking 90% out of? So starting with our hydrogen sulfide gas, or actually starting with converting both of these to mass values, 1 mole hydrogen sulfide gas has a mass of 34.085 grams, and 1 mole of oxygen has a mass of 32 grams. Now starting with our hydrogen sulfide, the ratio between hydrogen sulfide gas and sulfur is 1:8. 1 mole of sulfur is made using up 8 moles of hydrogen sulfide gas. (30) divided by the molar mass, and then divided by 8. 30 grams of hydrogen sulfide gas will produce 0.11002 moles of sulfur, and converting that into grams, 1 mole of sulfur has a molar mass of 256.52 grams. And so 30 grams of hydrogen sulfide gas are going to produce 28.2 grams of sulfur. Now going to our oxygen, the mole ratio between oxygen and sulfur is 4:1. 1 mole of sulfur requires 4 moles of oxygen to be made. And so 50 grams of oxygen are going to make 0.3906 based on rounding rules, 39062 moles of sulfur, because our last digit here is 8. Our last digit here is a 5, sorry. Looking at the sulfur. And now converting that into grams. (50 grams of oxygen can produce 100.2 grams of sulfur. And so, based on the values that we have here, where is my marker? Yeah, so based on the values we have here, hydrogen sulfide gas has to be our limiting reagent. Our oxygen, let me actually just check something real quick. Yeah, okay, cool. Our limiting reagent, we already labeled that. Our excess reagent is our oxygen. Jesus, I cannot spell right now. Excess, there we go. And the 28.2 grams is our theoretical yield. Now let's find out how much excess we actually have. Box in the wrong number. We can only make 28.2 grams, which is 0.11002 moles. Again, our mole ratio is 4:1, so we are going to flip what we have here. 4 moles of oxygen are needed to make 1 mole of sulfur, and 1 mole of oxygen is 32 grams. .11002 times 4, and then times 32. To make 28.2 grams, we only need 14.1 grams of oxygen. 14.1 grams of oxygen. And so we have 50 grams to start with. We only need 14.1. And so we're going to have 35.9 grams of oxygen in excess. And so now the last part of this, normally we would find percent yield after they have given us actual, but instead they have given us the percent yield already, and we need to find the actual yield. And remember, percent yield is equal to actual over theoretical times 100. And so, by knowing what our limiting reagent is and finding our theoretical yield, we have everything we need to plug numbers into our equation here to get that actual value. The percent yield, they're telling us for this reaction is 98%. And so some value x, which is our actual, over a theoretical of 28.2 times 100 will give us the value that we're looking for. Divide by 100 on both sides, and then multiply by 28.2 to get x by itself. 98 times 100, 98 divided by 100, and then times 28.2. And so our actual yield x is 27.6 grams. And so if you're given a percent yield, you can always work backwards. If you are missing any parts of this equation, you can, as long as you have everything else, it is now going back to algebra. You're able to solve for your actual yield if a percent yield is given to you. So a problem can give you an actual yield, or it can give you a percent yield. Either way, you can get the value that you're looking for based on our initial math up here. If you can calculate your theoretical yield, there's a lot of information that you can derive and actually get to for the rest of the problem. Just by knowing theoretical yield, you know information about your reactants, you can figure out how much excess you have in a problem, you can figure out percent yield, you can figure out your actual value if it's not given. A lot of information comes from our one value up here. That is the end of this workshop. If there are still any questions on the content that was covered in this recording, absolutely reach out to the Math and Science Resource Center here at John Jay to get more assistance. You can book an appointment yourself through John Jay Navigate, or you can go to the tutoring center on campus, room 1.94 in the new building, and someone at the front desk can help you book an appointment. You can book one-on-ones either in person or virtually, and there are plenty of tutors here who can help you understand the content better.